thanks again. And okay, first of all, this talk will have nothing to do with machine learning, which is I guess the initial reason why I'm here in Toulouse. But okay, it's going to have to do mostly with geometry, which is maybe somehow related. So what I want to talk about is I want to demonstrate some cases where stochastic calculus or Ito calculus can be helpful with proving geometric inequalities. And hopefully we'll have time to talk briefly about more or less 3 results or 3 scenarios. So the first one that I'll mention has to do with noise stability over the Gaussian space. So I'm just going to give some buzzwords here so we'll know what we'll have. So something around Gaussian noise stability, which has to do with, for those of you who know, with an inequality of Burrell from the 80s. The second thing we'll talk about is concentration inequalities or Poincaré inequalities for log concave measures. Of course, I will define all of this, so for those of you who don't know. And the third, hopefully, I will also have time to talk about an L1 version of the hypercontractive inequalities on Gaussian space. Okay, so hopefully we'll touch all of these. Let me just mention that the third one is a joint work with James Lee. Okay, so I guess the point where I want to begin, so I want to introduce some kind of stochastic moment generating process. We'll see what it is, but I want to start by recalling a very useful tool in analysis called the log Laplace transform. So what is the log Laplace transform given a measure mu on Rn? So in this whole talk, the setting will actually be Rn. If we define f of theta to be log of the integral of E x dot theta d mu of x, this thing is called the log Laplace transform of the measure mu. And it's useful because it has a few nice properties. It is a convex function. Since it measures exponential moments, it tells us something about the concentration of the measure mu. But I want to look at one specific property, which is probably known to most of you, that this thing is some kind of a moment generating function of mu. So it has the property that if you take the gradient of f of theta at theta equal to 0, then it's not so hard to see that you can, it's the gradient of log. You can okay, I guess you can just write that it's the integral of the gradient of E x dot theta mu of dx over the integral of the same thing without the gradient And the gradient means x goes outside here. We take a gradient, of course, with respect to theta, and this gives us that it's actually the center of mass of mu. So it's basically the integral of x d mu. So the first derivative of this thing is actually the first moment of the measure mu. Okay, this is not a very deep fact, but if you continue differentiating, you will see that the second derivative of f is, I guess you can already guess, it will be the second natural moment of the measure mu, or basically the covariance matrix of mu. Right? And if you keep differentiating, you get higher and higher moments, or in other words, actually you get higher and higher cumulants associated to the measure mu. And this is very useful because it lets us prove inequalities that relate moments of the measure mu to several concentration properties regarding the measure mu. I'm not going to talk about how to do these things simply because I don't have much time. What I am going to do, I'm going to define some stochastic construction that somehow has similar properties to this construction and will let us kind of establish new geometric inequalities. So basically, the construction I want to do is, actually I have another blackboard. So say we have Rn and we have a background measure mu. What I want to construct now is a measure valued process mu sub t. So suppose t is, we understand it as some evolution in time. So we have a time axis, and I want to define a measure mu sub t for every t by the following equations. So let's call d mu sub t to d mu at x. Let's just give it a name. Let's call it f sub t of x. And f sub t will satisfy the following equations. So f sub 0 of x will just be 1, meaning that we start with the measure mu at time 0. And then I want to consider the equation d f sub t of x is f sub t of x times x minus some vector at, which we will define in a second, times the increment of a Brownian motion. So here we think of Wt as a standard Brownian motion. And I just still need to tell you what At is. So At will just be the center of mass of mu t. So it'll be the integral of x with respect to mu t, so which I can write like this, ft of x d mu x on Rn. So just for those of you, so this is of course a stochastic differential equation. For those of you who feel slightly uncomfortable with Ito calculus, from here and on you can just think of the following thing. So this is just, I mean, if you feel comfortable with stochastic calculus, great. If not, just think about dt as some very small number, fixed very small number, I don't know, 1 over a million, and so this is a fixed number. And think about dwt, so the increment of a Brownian motion, just think about it as some Gaussian with covariance matrix square root of dt times the identity. So what do we do here? We basically start with density 1 at time 0. And what we do to our density is at every time step, we take it and we multiply it by a linear function. This is a linear function of x, whose gradient has some random direction distributed with respect to a small gradient. So in the end, as time passes, what we do is we start with a constant function, and we keep multiplying it by linear functions with random gradients. This might look kind of odd, but I claim that it has many properties which are kind of related to this moment-generating thing here. So any questions about the definition, first of all? Okay.
How can we prove that it exists, the solution?
That's actually a very good question, which I prefer not to touch. I mean, I will comment about it in a few minutes. Hopefully, I will remember to. The answer is you cannot. I don't know how to define it like this. But there is another definition which is less intuitive and is actually possible. But yeah. Okay, so some properties of this construction. The first property, I claim that if mu is a probability measure, then mu t is also a probability measure for every t. And the reason is that if I differentiate the integral of mu t, d mu t of all of Rn, this is equal to d of the integral of ftx d mu of x. I can put the differential inside the integral and use this formula, which gives me the integral of x minus at dwt ft of x dx. But now really, what is the integral of x ftx dx without this at? This is, by definition, exactly at. Right? So what I get is really at minus at times the integral. If I take at outside, then I get something like this, dot twt. But as long as mu t of Rn is 1, then this is 0, which means that this is just 0, which means that the measure of all of Rn does not change. So mu t remains a probability measure. Second property is, okay, very simple. For all measurable subset A of Rn, mu t of A is a martingale. And the reason for this is very simple. If you just look at a fixed point x, then the density of mu t at x is by definition.
I'm not completely convinced by your argument.
Which one?
Yeah, this one.
This one.
But you are using the fact that it is 1, that's what you want to prove. So usually you will use a 1 value.
So as long as it's 1, its differential is 0, and I mean, yes, you kind of still have to integrate this thing.
But you end up with the evolution, which is f prime is the square root of f, and you have to prove that such a solution is...
Yeah, I agree. I agree. There is some, yes, you have to justify some technicalities here. I completely agree, but let's, sure.
Just to see.
Yeah, yeah. But it works.
Hey.
No, that's a really good point, actually. So why is it okay? Or? So why is this a martingale? Just because the density at every x is actually a martingale. So definitely the measure of every set, which is just the integral over the set of the density, will still be a martingale. And the third property is that this measure has some kind of moment generating that it's moment generating in the following sense. So let phi be some test function. So some function on Rn, then we can calculate d mu t of phi, or d, okay. I want to understand mu t of phi as just the integral of phi over Rn with respect to mu t. Is that okay? So what is this? So I'm doing some calculations, but very soon you'll see that they have a point, okay? It might look kind of vague now, but so it's d of the integral of ft of x d mu x, which is the integral of x minus at dwt, ft of x d mu x. All I did now is I just used the definition of dft. I put the d inside the integral and just wrote what the definition of dft is. Oh, sorry. Thank you. Which I can equivalently write as the integral of phi x minus at d mu t of x. All of this thing times dwt. So what we really have here is the center of mass of this measure phi d mu t, right? Moved, normalized so that the center of mass of mu t is at 0. So this is some kind of first moment of phi with respect to mu t. So let's write this as m. Okay, I guess let's give this a name. This, I want to call it the 0th moment, m0 t of phi. And this I want to call it the first moment, m1t of phi. And it is actually a first moment. It's the integral of x with respect to this background measure. Okay? And if we keep differentiating, I think I'll bore you if I actually do this, but I guess you can believe me that every time I take the differential of something here, then the differential actually goes inside the integral, and I get d of ft, which tells me that I have to multiply again by the function x minus at. So every time I take the differential, I multiply again inside the integral by some linear function. So every time I do it, I basically get higher and higher moments of the function, right? This is a pretty simple fact. So I guess you'll believe me that if I tell you that dm1 t of phi is, well, it's the second moment, so it's some kind of covariance matrix. Let me write it. So it's really the integral. What you get is something like this, phi minus mu t of phi. So it's something normalized to have integral 0. But what I get here is x minus at to the tensor power 2 d mu t of x. So this is some kind of covariance. It's really, I can understand this as, okay, it's a slight abuse of notation, but it's really the covariance of phi mu t in some sense. And if I keep differentiating, I get higher and higher tensors. So I get all of this thing times dwt. Basically, the differential of every moment is the next moment times the increment of the Brownian motion. Okay, we'll understand this a bit better in a few minutes when I give you applications of this. So I guess this thing, I can give it a name. I can call it m2t of phi. So this is the second moment of this process. Good. So now we made some definitions and calculations, and we basically have no idea what they're actually good for. So let me give you the first example. So the first example will actually be kind of simple because I will take mu to be the standard Gaussian measure. So I'm going to do this evolution of measures beginning with just the standard Gaussian measure, and let's see what we get. So actually, this is one last calculation before the actual example. So what I can, no, actually, okay. Let me first formulate the theorem to give you a motivation for this. So I want to do the following definition for a function phi I want to define the heat operator or Gaussian convolution operator T sub rho of phi to be the expectation. So T sub rho of phi at a point x, I want it to be the expectation of phi at root rho times x plus root 1 minus rho times a standard Gaussian vector. So I guess most of you have seen this operator. It basically just takes a function and does a convolution with a Gaussian and renormalizes it under a slightly different parameterization. This is exactly the Ornstein-Uhlenbeck operator. And we'll also define a quantity called S sub rho, or the rho stability of a subset A. So for some subset A in Rn, I'm going to define this as just the integral of T rho of A at the point x squared with respect to the Gaussian measure. So this is just the standard Gaussian. Okay? Let's try to understand for a second what this definition means. So, given some subset A of Rn, what this measures is the following. It's really, I take a random Gaussian point. Let's say it fell here. And then T sub rho of A really gives me the probability that if I take this point and apply some noise, the point will still be in A. So it's really like the convolution with some small Gaussian. And if I take the square of this, then what it really means is the probability for two independent perturbations of this point to both fall inside the set A. So what I can think about is this white point is just a Gaussian point. The two purple points are just noisy perturbations, and I'm measuring the probability that two noisy perturbations, so two correlated Gaussian points, fall both inside the set A. This is called noise stability because it kind of measures the probability to stay inside the set after applying some small perturbation. So intuitively, if A is just some kind of cloud of little sets, I expect this thing to be small because the fact that the first point fell in A doesn't say anything about the fact that the second one is in A. And if A is kind of like a big chunk of mass, then I expect it to be kind of stable. Okay?
You will not say anything about the calculations that that's so the
Fraction
function. Yes.
Again?
You were reasoning as there is no square root of rho. You find
Yes. I mean, it's just a matter of normalization, right?
No.
Oh.
Your picture is not right because you should put 0 somewhere. Because 0 is not...
Yeah, I agree. I mean, it's really like the perturbation is not according to the actual Euclidean heat flow. It's according to the Gaussian heat flow that has some drift to the origin. That's right. So this Gaussian is a little closer to the origin. But it's like this. That's true. So there's a theorem of Burrels from, I think, 85 or something, which says the following: if we have two sets with the same Gaussian measure, and one of the sets is a half space, then the stability of the half space is at least as big as the stability of the other set, which is not necessarily a half space. In other words, half spaces maximize noise stability. It's also pretty easy to see that as rho goes to 1, as this noise goes to 0, the limit case of this theorem is just the Gaussian isoperimetric inequality. So the probability for both these, for one point to be in A and the other not to be in A, if they're very close to each other, it's just basically the surface area of A. So what I want to do is try to give a pretty simple proof of this theorem given this construction we just did. The first thing I want to observe is that T rho of my function phi at x, I can easily change the definition and instead write something like this. It's the expectation of phi of a Brownian motion at time 1 given that the same Brownian motion at time rho was equal to root rho times x. This is pretty straightforward because if I fix the Brownian motion at time rho, that the difference between the Brownian motion at time 1 and the Brownian motion at time rho, so the distribution of W1 given W rho is just W rho plus root 1 minus rho times the standard Gaussian. If you plug this into there, you will get the same thing, right? And what I claim is that if we go back to the construction of these measures mu t, then what we really have is that T rho of f of phi, sorry, or basically this stability is just equal to the expectation of mu t. So these measures mu t are exactly follow this law. So I claim that this equality holds, and the reason is, well, we can just differentiate and see, but the point is the following. If we take let me just remind you that d of ft if we calculate d of the logarithm of ft using Ito's formula, what we get is d of ft, so the first derivative of log is just 1 over x. So we get over ft of x. And the second derivative of log is minus 1 over x squared, which gives us minus 1/2.
You want to recover the exponential of the Eldan, no?
Yes, exactly. I want to see what happens to the exponential of this change of density ft. Okay? Because I just want to understand what are these measures that I'm getting.
You have such an equation, dmt with mt martingale, it's exponential of the Eldan to get, no?
I'm not sure what that is.
No, I think it's...
Oh, yeah, I see what you're saying. I mean, you can just use this formula for the exponential of a martingale. Yeah, but okay, it's really the same. Yeah. So if I just plug in what dft is, what I get is, so this ft exactly cancels out with this ft, and I get something like x minus at dwt. So I get some linear term. And here what I get is basically the square of this linear term. So it's really minus 1/2 x minus at square. Again, if I take the square of this, it cancels out with this dt. So what we see here is that log of ft is really always a quadratic function, which means that the change of measure is always just basically some Gaussian density. What I get at every time is the original measure mu times some Gaussian density with some covariance centered somewhere. Okay? And I can easily calculate what this Gaussian density is. And if we do a slight renormalization of this, again, I don't want to bore you with calculation, so I'm just going to wave my hands a bit and just tell you what we get. But if I just put something like this here, I multiply this by some function of t, this is just some kind of change of time, then what we really get here, so I get here 1 minus t squared, and here 1 minus t. And what we see is that this, if I take this quadratic term and integrate it, what I get is that ft is e to the something, which is a quadratic thing, that has a linear term, but the quadratic term is the integral of this, so we get something like 1 over 1 minus t x squared. So the quadratic term looks like this. It's 1 over 1 minus t, which means that the covariance of this Gaussian, there's also like two more terms here that I don't write, which will basically determine the shift of this Gaussian. But the variance of this Gaussian is really so it's really a Gaussian with covariance 1 minus t times the identity. So all this process does is it starts with a standard Gaussian, and then it takes the Gaussian and it moves it around. Mu t is a Gaussian for every t with decreasing covariance matrix, so it kind of focuses down. Okay, and it actually looks exactly like this process, like W1 conditioned on, well, W rho as rho increases, right? I guess it's kind of easy to believe. And if you plug this fact, well, to this, you just get this claim. I mean, I could show you the exact calculation, but I'm not sure it would actually contribute to anything. I guess at this point, you can kind of believe me. Okay, so in the end, what we get is that the stability of phi is the indicator of some set, is really just the expectation of this thing. But if you remember, mu t was actually a martingale. I mean, it's kind of obvious from this also. So using orthogonality of martingale increments, what we also get is that this is just the expectation of the quadratic variation of this process mu of phi at time t. Should I define quadratic variation or? Basically, okay, quadratic variation is just the sum of squares of the martingale increments, right? Okay, so we constructed some kind of process, and basically this definition boils down to quadratic variation, but now we remember that the first moment of that, basically the differential of mu, so now we basically remember that this was a moment generating process. Property 3, I think. Yes, sorry. Yes. Thank you. So at this point, we remember that d mu t of phi was what we call the first moment, m1t of phi, which is just, well, the integral something like that. So the rate of change of this martingale has to do with how far the center of mass of phi is from the center of mass of mu. And in other words, if we look at the quadratic variation of this thing, then by definition it's just the rate of change square. So it's just the square of this, which is just equal to the square of this integral. Okay? I'm going slower than I had thought. So at this point, let me just wave my hands a little and tell you why this kind of almost proves Burrell. So we had our set A, which is not a half space. And we had another set H, which is a half space. And we want to compare the rate. Basically, you see that comparing those two things boils down to comparing how far the center of mass of A and of H is from the origin that, let's say, is here. And it's a pretty easy geometric claim to see that if the measure of A is equal to the measure of H, so if we have this, then the center of mass of H must be at least as far from the origin as the center of mass of A. And the reason is that if both centers of mass are pointed in this direction, then if A is not a half space, then I can always take mass and move it this way and make it a half space, right? I can always take this mass and put it here, and this mass and put it here. And what I do is I just take the center of mass and make it farther. And I can do it as long as A is not a half space. So really, point-wise in time, we have that the quadratic variation of this martingale is bigger when the set is a half space. This is true as long as I keep both martingales, the one corresponding to A and to H, having the same size. And this is done via some kind of coupling argument that I don't want to touch right now, but it's actually not so difficult. But the point was, everything is kind of using this moment generating property, everything is reduced to something about how far the center of masses are from the origin. Okay? And actually, using this method, so this gives a pretty, I think, simple proof of Burrell, but also using this method, actually more can be said if you take these processes, this m1 of t, and differentiate it again. So it turns out that if it turns out that if A and H are kind of far apart together, far apart from each other with respect to this quantity, to this m1, you can actually differentiate m1 and look at the rate that this quantity changes in time, and what you get is some kind of something that has to do with the covariance matrix of these respective sets. And when you analyze the covariance matrices, you see that if A is actually close to a half space, then the covariance matrices are not so far from each other, which means that these processes, the M1 that is associated with H and the M1 which is associated with A, are not moving so differently from each other. And this gives you something about basically a second order inequality of this form. It basically tells you that if these things are far apart at time 0, then they will stay far apart at, well, like a non-negligible interval of time. And what you get is that this difference, let me just tell you more or less what you get. You had that S rho of H minus S rho of A is not only bigger than 0, but it's bigger than, well, up to some log factors, it's bigger than M1 0 of A of H minus M1 0 of A. So somehow the difference between the first moments of the sets dictates the difference between the stabilities. So this is like an improved Borel estimate that you get from this technique. And let me just point out that this improves a bound previously proven by Mossel and Niemann, who get kind of the same thing but with a different power in one of the sides. Okay. So that took longer than I expected, but let me move to, hopefully at least I'll be able to talk about one more thing, which is, how much time do I have left, by the way?
20 minutes.
Okay. So concentration of Lipschitz functions on log concave measures. So this is the second application of this process. What we want to try to do is the following. So we're given some probability measure mu on Rn. And what we're interested in is proving some kind of concentration inequality. So what do I mean by a concentration inequality for Lipschitz functions? So suppose that phi is 1 Lipschitz. What we want to show is an inequality that looks like this. We want to show that mu has the property that the variance with respect to mu of phi is bounded by some constant associated with mu. So the point is, we're given some measure mu, and we're interested in proving this inequality for every one Lipschitz function with the best possible such constant. Okay? So now I want to somehow use this process mu t, which we constructed, and the way to use it is actually very simple. So let's recall that mu t of phi is a martingale. So we really have that the variance of mu infinity of phi, so mu infinity is just the measure as time goes to infinity, is, well, it's just the expected quadratic variation until time infinity, again, because this is a martingale, right?
Does it converge?
Very good. So I expected this is exactly the question I wanted right now. So let's recall that according to this calculation here, we know that mu t are Gaussian measures. Mu t with respect to mu, the change of densities, are just Gaussian densities, which have smaller and smaller covariance. Okay?
You have to remove the 1 minus t.
Yes, so the 1 minus t is really just a change of time. With the 1 minus t, what you get is that by t equals to 1, you get a Gaussian of variance 0. Without the 1 minus t, you get it for t equal to infinity. This is a pretty easy calculation. Okay, the point is that you get this quadratic term becomes bigger and bigger and goes to infinity. Okay? Which means that the covariance has to go to 0 under some mild assumptions on mu. Again, this is a bit of a delicate point, but it's not such a problem. Okay? Kind of believable? So you get the convergence toward a Dirac mass or not? Good. So mu infinity, so it could explode before time infinity, but let's say that if it becomes a Dirac mass at some time, we just keep it a Dirac mass forever. Okay? And basically what we get is that mu infinity is just converges to a Dirac mass at a random point x. But since the measures mu are martingales, then it's pretty easy to see that x must have the distribution of mu. So we really start with the measure mu and we converge to some Dirac mass which is distributed again according to mu. This actually induces like some score code embedding of mu, of basically the Brownian motion into mu, if you like. Okay? At least in one dimension. Good. So basically saying this, what we said here is that this variance of mu infinity of phi is equal to the variance mu of phi, which is the quantity we're interested in bounding. Okay? So we're really interested, again, in bounding the quadratic variation of this process. And since it's moment generating, we know that this is equal to the expectation of, again, some center of mass process. So it's really the expectation of this integral x minus at. So again, I'm using this first moment property. And here I have phi d mu t of x square. And also I have the integral with respect to t, so I have something like this. I just used, again, the formula for the first moment. And at this point, it's a pretty easy application of Cauchy-Schwarz to say that, well, instead of this integral, I want to consider the product of integrals of this thing square and this thing square, which basically gives me something like the expected integral of, well, maybe let's do one more step before using Cauchy-Schwarz. So this thing is a vector, and let's say it's pointing in some direction theta t. So let's define theta t as the normalized direction of this vector. What I mean is that instead of looking at the norm square of the vector, I can just consider x minus at dot some theta t. Of course, there is some direction which maximizes this thing. So I get this. And at this point, if I use Cauchy-Schwarz, then I get phi square, which is basically just, again, the variance of phi. So it's smaller than the integral with respect to t of the variance mu t of phi times the integral of this quantity squared. But this quantity squared I can also always write as the covariance of mu t times phi. I know this is not a positive measure. This is a slight abuse of notation, but it doesn't matter so much. And take the operator norm. Okay? This thing just bounds the integral of the square of this thing with respect to mu t. Sorry, there is no phi here. Phi went here. So if we move this thing to the other side, it's pretty easy to see that it's really enough to bound the process covariance of mu t operator norm. Okay, we get something like, yeah, I guess. Does that make sense? If this thing is small, then we will get some bound for this thing. But this is kind of nice because this does not involve phi anymore. It's some kind of process associated with the measure mu. And if this process is bounded, we get a bound for the variance of every phi. Okay? So now we have to look at this process, and this process is really a second moment process of mu t. And the analysis of this process has to do with, so we can just differentiate it and use this moment generating property, and we get that d of the covariance matrix of mu t is some kind of, okay, it's some expression involving third moments. Okay? And somehow, okay, I have, I guess, 2 more minutes, so.
2 more minutes to use the assumption that it's working.
Yes, very good. So, the point is, we can't, okay, good. So how do we use the fact that it's log concave? You remember that we had the fact that log of ft is some Gaussian measure, e to the minus some linear thing minus something involving t x squared. And we have some very nice thing by basically a theorem of Braskamp and Lieb saying that if mu is log concave, then mu t will be more log concave than some Gaussian density, which means we can stop this process at some point in time t and already know that the measure will satisfy some kind of concentration inequality. Okay, this is, okay. This was a lot of hand waving, but I guess what I wanted to show you is how basically concentration inequalities for functions can be reduced to estimate about moments of this measure-valued process. Okay, I guess I have to stop here.
Are there any questions beyond the if in Borel's theorem you have functions rather than sets?
Yes, so basically, okay, all the analysis works the same, only we had this geometric claim saying something about the sets that maximize this first moment expression. So for functions, you would just get, I guess, linear functions. Depends how you normalize it. And, okay, the conclusion will be kind of trivial. It will be that the functions that maximize noise stability are just functions which are concentrated on like the first degree Hermite coefficients. So
you don't get this Borel theorem with the Gaussian symmetrization of the function?
So I'm not sure.
Basically that the analog of your noise stability is upper bounded or lower bounded, I don't remember, by the Gaussian symmetrized function of the function you started.
So is that the Bobkov thing?
This is Borel theorem. You did it for functions.
I see. So actually, I'm not sure. I mean, I don't remember what the inequality is right now. So we can look at it.
So you work in a linear context, but if you are in a manifold, then you will use some kind of fresh mean that there is no mean, but you can nevertheless, I think, consider the process, but not define the AT. You have looked?
Yes, but even the process, I don't know what multiplying by a linear function means over a manifold. I mean, just like there's no analog for the log Laplace transform, which multiplies by an exponential, right? It's not so clear.
There is some variance of phi with respect to mu t in your inequality. So how do you manage this term?
Yeah, that's actually. So yes, I cheated a bit here. But I mean, it's okay. It's 2 more lines. I can write them down if you want, or maybe I'll do it later. Yeah, I know. That was a bit of a cheating here, but it's really you just look at this variance, and what you see is that its differential with respect to t is smaller than something that has to do with this thing. I mean, okay. That's a good question. I mean, I don't know how this can be used for the 2 different sets case. It's not clear.